Hello, welcome to Chapter 10, first chapter and first section of second semester. We're going to learn about statistical inference and confidence intervals today. Statistical inference provides methods for drawing conclusions about a population from sample data. And this will make more sense as we do some of it. But the goal with inference is to figure out what our data say about an entire population. Because we can't survey everybody in our population, but we can take a guess at what they would think. Now, a university wants to find the IQ of their freshman class. They obtain an SRS of 50 students out of 5,000, and the mean IQ of the group is 112. What can the university say about the mean IQ of the entire freshman class? Now, how would the sample mean vary as they choose more groups of 50? Well, we know that since it's 50, it should have a normal distribution, because since n is greater than 30. So the sampling distribution should be normal. The mean should equal the mean IQ of the freshman class. And the standard deviation, we know is going to be the standard deviation of the population over the square root of n. So I already started talking about this. Now, suppose we know the population standard deviation is 15, then the standard deviation for the sampling distribution is going to be 15 over the square root of 50, which equals 2.1. Now, the essential limit theorem tells us that the mean is going to be, or the distribution is going to be relatively normal. So to estimate mu, we can use x bar from a random sample, and x bar probably is not equal to mu, so our estimate has some error in it. In repeated samples, the values show x bar follow approximately normal distribution with a mean of mu and a standard deviation of 2.1, and about 95% of that data is within two standard deviations of the mean. So 95% of the time, the mean IQ score, x bar, will be 4.2 standard deviations from, or 4.2 points from the population mean. So wherever x bar is within 4.2 standard deviations of mu, mu is within 4.2 standard deviations of x bar. So the unknown mu lies between x bar minus 4.2 and x bar plus 4.2 in about 95% of samples. So if we estimate mu lies somewhere in between the interval of 107.8 and 116.2, we would be calculating this interval using a method that captures the true mean about 95% of all samples. Alright, so this is what we call a confidence interval and confidence level. So our confidence level on the previous problem was 95, and the range that they gave was an interval. The confidence interval is collected from the data, usually in the form we have an estimate, and then plus or minus a margin of error. And you'll see this with presidential polls, or really any polls. They'll say Romney is winning at Florida 0.4. He's polling at 40% of the population, plus or minus 3. That plus or minus 3 is the margin of error. The 40% is the estimate. All right. Now the confidence level, which gives the probability interval, will capture the true mean in repeated samples. So it's a success rate for that method. So in the 95%, so we don't know the sampling distribution when we take one sample. Our data could be here, 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 way out here. We'd have no idea. But we know 95%, so here's 20 samples, and 95% of the time, the error that we put in the 95% confidence interval will mean that the bars will cross the true mean. Now, it will happen every once in a while that we'll take a random set of data and get information that doesn't capture the true mean. But that should only happen about 5% of the time in a 95% confidence interval. Now, conditions for constructing a confidence interval. The construction of a confidence interval for population mean, mu, is approximate when the data comes from an SRS, the sampling distribution is approximately normal, and the observations are independent. So when we're sampling without replacement, we got to say that the population size is at least 10 times our sample size. Now we need to figure out this thing called Z star. Z star is the Z value at which the Z value where we know the probability of everything underneath it. So for an 80% confidence interval, let's assume that 80% is in the middle. So if this is 80% of our data, then there will be a 10% over here and 10% over here. So what we need to do is find the z-score over here. So we want our z-score on that end. So there's 90% of the data up to there. So we can do inverse norm of 0.9. And that should give us our z star. Now, for 80%, our z star should be 1.282. Now, if we do this for 80, 85, all the way up, pause the video and see if you can find these values. So, and 99 is 2.576. Now, to find 85, these are all what I just had in my book, which were easy to find. If this 85% of the data, 15 is on both sides, so that means we have a 0.075 there. So this is 0.925. Take the inverse norm of 0.925, and it should be somewhere in between there, 1.4-ish. Alright, so when we want to do our confidence interval, we're going to do x bar plus or minus z star times sigma over the square root of n. So here's an example. A manufacturer of high-resolution video terminals must control the tension on mesh fine wires that lie behind the surface of the viewing screen. The standard deviation is known to be 43 volts. Here are the tension readings from an SRS of 20 screens from a single day. Construct a 90% confidence interval for the mean tension, mu, of all screens produced that day. Now there's 4 steps when doing a confidence interval. First, we need to talk about the parameter, then talk about the conditions, then do the calculations, and then finally interpret them. So the first thing we want to do is talk about the parameter. What are we trying to find? Well, we want to find the mean of all tension readings in a particular day. Now we have to check the conditions. It says the data comes from an SRS, so we can say data comes from an SRS. Wonderful, that's already done. Normality. We need to figure out if this is normal. We only choose 20 screens, so we can't use the central limit theorem. So we're going to have to graph these. So plug all of this data into your calculator and then make a box plot. Alright, once you have all the data in there, then graph it, and you should have a box plot that looks something like this. Alright. Now, This is about 250, 300, 350. So since this box plot is relatively symmetric, we can say that the data is approximately normal. So we want to write that. The box plot is symmetric. So sampling distribution is approximately normal. All right. Now the third condition is independence. So we're sampling without replacement, so we need to check that n is greater than or equal to 10 times little n. So that's the population has to be bigger than 200. So we'll just have to make a statement that says we assume there are more than 200 video terminals being produced. Alright, so now we can move on to our calculations. So the first thing we need to do is write our formula. And if I do one variable stats, we can find our mean. And our mean was 306.3. Now our z-star for 90% confidence interval is 1.645. Multiply that by our standard deviation over the square root of n, which is 20. And we'll get 306.3 plus or minus 15.8, which means that we have a range from 290.5 to 322.1. So now we just want to interpret that. We want to say we are 90% confident that the true mean tension is between 290.5 and 322.1 for that day. All right, and there we go. We are done with our first confidence interval. Now keep in mind we need to write it up just like this in order to get full credit. All right, now you guys try one. Suppose you want to estimate the mean SAT score from for more than 385,000 high school seniors from California. You give an SRS to 500 California high school seniors. The mean of the sample is 461. Assume that the standard deviation is 100. Now construct a 99% confidence interval. Well, we want to start with the parameter. We want to estimate the mean SAT score of California seniors. Now we look at the conditions. Data comes from an SRS. We have 500, so since n is greater than 30, the sampling distribution is approximately null. And we want to check to see that n is greater than or equal to 10n. So the population is at least as bigger than 5,000. And it says that in the problem, so observations can be treated as independent. Independent because big N is greater than 5,000. And it tells us that big N is 385,000, so we're pretty safe. Now for the calculations. I always like to write my formula first. So our X bar was at 461. All right, now if you understand how to do these problems, pause the video and see if you can do this one on your own and see if you get the right answer. Hopefully you have completed this and we can go through how I would do it. So suppose you want to estimate the mean SAT math score for more than 385,000 high school seniors in California. You give the test to an SRS of 500 California high school seniors. The mean of your sample is 461. Assume that the standard deviation for the population is 100. Now we want to construct a 99% confidence interval to estimate the true mean. All right, so the first thing we need to do is figure out what our parameter is. What do we want to estimate? And they talk about it up here. We want to estimate the mean SAT math score for the high school seniors in California. So we'll write that. We want to estimate mu, which is the true mean score on SAT math for California high school seniors. Great. Now, once we know what we're trying to estimate, we have a sample, and this is the information for our sample over here. But before we get into finding any calculations, we need to look at the conditions. Now, first off, we can look for SRS, and it tells us that the data comes from an SRS, so we'll just say the sample is from an SRS. Now, we like to know that because now we know we can generalize it to the entire state. Next thing we want to look at is normality. Well, there's 500 scores. 500 is greater than 30. So the central limit theorem tells us that the sampling distribution would be approximately normal. Now there's one sampling distribution is approximately normal. I wanted to get ahead of myself. Now remember, if you just say normal instead of the word approximately, That's a big mistake. It's not going to be normal. It's going to be approximately normal. And now the last thing, we want to check for independence. Since we're sampling without replacement, that's an N, we want to check to see that the population is at least 10 times as big as the sample. So our sample is 500, so we need to know that there are more than 5,000 high school seniors, and California is a pretty big state, so just say there are more than 5,000 California high school seniors. All right, now that we have the conditions and the parameter taken care of, now we can worry about the calculations. The calculations, we want to look at our mean and add or subtract our z star times our standard deviation or standard error. Now the mean of our sample is 461. Our z star for the sample is our z star for the 99% confidence interval. And that value is 2.576. And we're going to multiply by this by the standard deviation of the population, which is 100. Now we divide that by the square root of 500. So now we just take out a trusty calculator. 100 divided by the square root of 500 is 4.47, and I multiply that by 2.576. So I have my margin of error being 11.52. So we have 461 plus or minus 11.52. Now when I subtract 11.52 from 461, I get 449 points, let's just say 449.5, and then when I add it, I get 472.52. So that is our confidence interval. Now our interpretation. Now we are 99% confident that the true mean SAT score for California seniors is between 449.5 and 472.5. All right, now that is our lesson. Make sure you have this whole write-up. Even though the calculations are what most people think of in a math problem to be the most important, there's only one part of these 4 parts that are needed in confidence interval. Hopefully you can get through the homework. Good luck.